Hello, in this video we are going to see the relationship between the properties of several types of solids and their chemical structure. The most obvious distinguishing feature of any solid is the fact that they are rigid. And you can see in this image a piece of false gold or pyrite. Like any typical solid, it's hard, it's rigid, especially when you compare it to a liquid or a gas. On a microscopic level, this corresponds to the presence of very strong forces between the atoms or ions or molecules, whatever are the specific individual particles of the material. And so the position of each of these particles is relatively fixed. And the motion of those particles is quite limited. The only movement within a solid crystal lattice are the relatively limited vibration about an average position. So this restricted vibration is due to the tight packing of the atoms. Thus, we often think and speak of crystalline solids as having atoms or ions or molecules in very fixed position. Solids can broadly be classified as crystalline and amorphous. Crystalline solids, they have regular ordered arrays of components held together by uniform intermolecular forces that are the same in every direction, whereas the components of amorphous solids are not arranged in such a regular way. So in this model, we're trying to understand how the characteristic properties of crystalline and amorphous solids relate to their structure. The faces of crystal can intersect at right angles, and you see in galena that is a core of lead and sulfur, or at other angles, as in the example of quartz, that's a silicate. For obsidian, you can see that the cleavage surface, when you break it, tends to be typically curved, so that it lacks that distinctive geometrical structure. So this picture represents the effect of applying a stress to an ionic compound, where the crystalline structure is a result of the attraction between negative and positive ions, represented here with different colors and different numbers 1 and 2. So the application of a stress force, initially you will encounter a strong resistance because you're trying to overcome the strong electrostatic attraction between positive and negative charges. When eventually the stress is strong enough, you will shift the relative position of the ion so that now same charges are facing each other, and this will create a strong repulsion, thus causing the breakage. But the cleavage will happen along a very defined and neat plane. There will be a very sharp melting points because of the very homogeneous distribution of the forces that are the same in every direction are such that the amount of thermal energy needed to break every interaction will be the same, and so all the breaking will happen simultaneously. When exposed to X-rays, and that's a technique to investigate the internal structure of a solid, crystalline structure produce very distinctive regular patterns. As opposed to amorphous solids, again, we have the example of obsidian, that when cleaved, broken through curved surfaces, they lack defined patterns when exposed to X-rays. And because of the irregular distribution of the forces inside the solid, they tend to soften slowly over a large temperature range. So we can classify crystalline solids into 4 main categories: ionic, metallic, covalent, and molecular. So we have already talked about ionic solids when we'll be talking about covalent bond versus ionic bond. We will just recall that the ionic crystal structure consists of an alternation of charged positive and negative ions. The ions could be monatomic or polyatomic. It doesn't really make any major difference in this reasoning. Ionic crystals are hard and brittle and have very high melting points. Ionic compounds do not conduct electricity as solids, because to conduct electricity you need the presence of moving charged particles, and in the ionic crystal the position of the ions is fixed. However, if you melt them, then the mobility of the ions increases, and in this situation they can conduct electricity. They can also conduct electricity when dissolving water, because at that point the ions becomes independent, and the dielectric effect of water kind of contrasts the attraction between, acts as a shield in the attraction between the different ions. So let's look at metallic solids. At the beginning of the semester, we learned to write the formula, for example, of hydrogen or oxygen as H2 or O2 in order to represent that they are diatomic molecules. Noble gases were represented simply by their symbol because they have a monatomic structure. So when we write, for example, iron or sodium in this form, that does not mean that they are structured as isolated and independent atoms. The fact that a block of iron displays as a solid implies that all of those atoms of iron are kept together by some sort of attractive forces. Same for a piece of sodium. So let's look at the electron configuration of sodium, for example. So we have learned to distinguish between core electrons, the ones that are represented here in black. So these are the core electrons, and then we have the valence electrons represented in red. So for sodium there is one valence electron. So what happens is that in a piece of solid sodium you have an ordered distribution of the positive ions, the ones that are a result of losing that valence electron, and the valence electrons that are represented by the yellow smaller dots are delocalized, so they don't belong anymore specifically to one specific atom of sodium, but are rather shared among the entirety of the sodium atoms, and they become what is called a sea of electrons that keeps together the whole structure like a glue. So what keeps together the piece of solid sodium is the attraction between this array of positive ions and their electrons. But the electrons, being delocalized, retain quite a lot of mobility. So because they can move around, this makes a solid piece of metal a good conductor of electrons. So these slides kind of summarize the characteristic of this sea of electron type of model. Metals tend to have high melting points and high boiling points, and this suggests that the bonds between the atoms is quite strong. Even a metal like sodium that melts about 100 Celsius has a considerably higher temperature than the preceding element, neon, in the periodic table. So many properties of the metals can be explained relying on this model of the sea of electrons. We can change the shape of a metal without breaking it, so we say that the metals are ductile and malleable, because the electron sea acts almost as a lubricant between the layers of positive ion, and the metal ions can kind of slide past each other. They are good conductor of electricity because these electrons are quite mobile, and they can be and they can therefore move under the effect of an electric field. They are also good conductors of heat because the delocalized electrons can carry kinetic energy through the lattice, and they have a shiny appearance because the electrons on the surface can bounce back the light at the same frequency as the light that hits them. So it's easier to melt a metal than to melt an ionic compound, and their higher boiling points are much higher. There are interesting periodic trends. So let's look So we have in pink elements from group 1 and in blue elements from group 2. And there is kind of an, let's say except magnesium, there is kind of a nice regular trend. So first of all, if we compare lithium with sodium, we see that it's easier to melt sodium. Sodium has a lower melting point and it's harder to melt lithium. This is due to the fact that lithium, as you might remember from the periodic trends, is smaller than sodium, so the atomic radius goes up. So atoms become larger and larger going down a group. So the smaller of a group 1 is lithium. Because it's so small, the attraction between the lithium ions and the electrons is stronger. So those electrons are, the whole structure is more tight and strongly kept together, therefore it's harder to melt. And the trends keep going down the group. If we compare lithium and beryllium, the difference is that in beryllium has a much higher melting point, so that's a huge difference. And that's due to the fact that in beryllium you have the ions that has 2 positive charges, and the electrons are twice as many that you have in lithium. So again, the attraction, it's much stronger, and this is keeping everything more tightly together. So this is an example of group 1 metal versus a group 2 metal that shows you the larger amount of electrons and the larger charge on the ions that explain the stronger attraction between the elements of the structure of the crystal, and therefore the higher melting point and boiling. So in the top part of this slide, we can see the comparison between melting point and boiling point of sodium, that is in group 1, magnesium, that is in group 2, and aluminum, that is in group 3. You can see an increase in the melting point that parallels the increase in the number of electrons in the valence shield, and a more, I want to say, consistent increase in the boiling point. The boiling point is somehow more representative, more correlated to the strength of the metallic bond, because melting point represents the transition between solid and liquid. So in liquid, the different atoms are still kind of staying together, so they're still having some sort of interaction, as opposed to boiling, where you have the transition from liquid to vapor, and in the vapor the metals are completely separated. So that's transition is more representative of the strength of the bond, and you see a marked increase there. At the bottom you can see the values for 3 transition metals, and we have markedly higher value of both the melting point and the boiling point, and this is because for transition metals you also have the involvement of the electrons in the d orbitals. So this makes the metallic bond stronger, therefore increasing the melting points and the boiling points. It also makes the structure of the crystal more tight. That explains the higher density of transition metal respect to metals in group 1 and group 2. So when we melt metals, the metallic bond is still present, and this is why the boiling point is actually a better guide to the strength of the metallic bond. So we can also have covalent crystalline solids, an example being diamond. In diamond, diamond is composed of carbon. Carbon has the ability to make 4 covalent bonds through sp3 hybridization, as we have seen in the unit about covalent bonds. And this implies a typical tetrahedral structure with 4 identical bonds, equivalent bonds in at an angle of 109.5. So each carbon has a covalent bond with another atom of carbon, thus creating a very ordered crystalline structure. And this underlying microscopic structure explains the difference between diamonds and graphite. So in diamonds we have these 4 equivalent bonds in a 3D structure with an sp3 hybridization. Each atom has a very fixed position, so this makes diamond very hard with a crystalline structure due to the order. If it's broken, it would break through clear cleavage, and diamond is not a good conductor of electricity because the electrons are a very fixed position in those covalent bonds. Graphite instead has an sp2 hybridization. So the three hybrid orbitals are used to make covalent bonds with other atoms of carbon that would be in the same plane. So in each plane you see that one atom of carbon is forming 3 bonds with other atom of carbon in the same plane. The non-hybrid p orbital that I'm highlighting in green is used to make this interaction between different planes. These are much looser interaction. The electron in this area are somehow more mobile and are delocalized. So this explains the good conductivity, electrical conductivity of graphite that can be used to make electrodes. And it also explains why graphite is soft, because you can move each plane respect to the other. So the last type of crystalline solids are molecular crystals. Molecular crystals typically consist of molecules at the lattice points of the crystals, and they are held together by relatively weak intermolecular forces. We will talk about intermolecular forces in the next presentation, in the next video. These intermolecular forces may be just dispersion forces, so don't worry now if you don't know what dispersion forces are, because we will talk about that, as I said, in the next video. They can also be, so they could be these intermolecular forces could be dispersion forces, or they could be dipole-dipole forces. Some molecular crystals, such as ice, in that case the molecules are held together by hydrogen bonds. Again, we will talk about hydrogen bonds. You can manage to make a noble gas liquid and then solid by increasing the pressure and reducing the temperature, in which case at the lattice points you would have the individual atoms of the noble gas rather than the molecule. But in general, in this type of solid, the intermolecular forces that are keeping the particles together are quite weak with respect to ionic or covalent bonds that we've seen for the other type of solids. Therefore, the melting and boiling points of molecular crystals are quite lower. They lack ions or free electrons, so they are poor electrical conductors. And that's pretty much all you have to know about solids. So we will see again for the next video that will be about specifically intermolecular forces.